Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. I'm Dr. Owusu, and this evening's session is going to be on analytical techniques, and of course we're going to be focusing on infrared spectroscopy and mass spectrometry at AS. And as usual, I will welcome all questions on either analytical technique over the course of the session. If you use the chat box to write your questions in, and I will be pausing at appropriate points to answer these questions for you. We will start by looking at what infrared spectroscopy is, and then we will move on to mass spectrometry. And for both techniques, we will be looking at why they are important to an organic chemist, and we'll be looking at what they are used for. What do they tell an organic chemist? Okay, so as usual, I will be connecting my tablet, and then we will quickly remind ourselves of what the syllabus requires us to know. So if you just bear with me for a second or two, I will connect my tablet and we will get going. Okay, so it looks like we're all set. You should see a screen with my title page. The first thing I want us to take a quick look at is the OCRA spec, and if I make that a bit larger, there we go, so you should be able to make out the infrared spectroscopy spec points. And of course we need to know why infrared spectroscopy is useful, so we need to know that it is used to identify different covalent bonds in a molecule, and some of those covalent bonds are shown here in the spec. And then, of course, how to interpret infrared spectra to allow us to work out the structure of an organic molecule. And then there are some more general applications, such as in breathalyzers, allowing so the law enforcement to identify people who have gone over the drink drive limit, for example. So again, that is the technology, well, the science underpinning that technology is infrared spectroscopy. And then we will move on to mass spectrometry, and again we will be looking at how mass spectrometry is used to allow us to work out the structure of organic molecules. So we will be looking at the significance of the molecular ion peak, for instance, and we will also be looking at fragment ions and what they tell us about the structure of a molecule. Okay, so let's look at infrared spectroscopy then. So we saw very briefly the spec point about what infrared spectroscopy allows us to find out, and of course it is to identify different types of bonds present in an organic molecule, or rather the different types of covalent bonds present. Okay, so we're identifying different covalent bonds present in a molecule. Okay, so some of the typical bonds that we can identify using infrared spectroscopy include the carbonyl bond, so C double bond O, and the OH bond, of course, which is what makes molecules, which is a functional group for alcohols, I should say. And we are also able to identify carbon-hydrogen bonds, and as you would know by now, most organic molecules will have CH bonds, and that in itself is not of particular use when identifying the structure, and I'll say a little bit more about why that is shortly. Okay, so the three typical bonds that you would see in an organic molecule, we can use infrared spectroscopy to identify. There are other bonds that will that can be readily identified using infrared spectroscopy, so nitrile groups as well, so C triple bond ends, and of course NHs as well. Okay, so all of these bonds will show up in infrared spectroscopy. So how does it work? Now, all bonds vibrate, so you can think of a good analogy for a bond, a covalent bond, is to imagine a spring with two masses at either end. Okay, and that spring vibrating between the two masses is what your covalent bond is. Now, if a covalent bond absorbs infrared radiation, it can be caused to vibrate even more. Like I say, if it absorbs at its resonant frequency, and the vibrations are even more, and we can detect the wavelength of infrared spectroscopy that is being absorbed. In other words, the resonant frequency in a spectrum. And different covalent bonds will absorb different wavelengths of infrared spectroscopy. Of different wavelengths of the infrared radiation. And that allows us to work out the different covalent bonds present in a molecule. Okay, so in answer to the question, how does it work? You want to say or talk about bonds absorbing infrared radiation. Bonds, it's covalent bonds. So they absorb infrared radiation at their resonant frequency. The frequency absorbed can be shown in an infrared spectrum. Okay, so any type of bond, so for instance, an OH bond will be vibrating, and if it is, or if it absorbs the correct frequency, its resonant frequency, it will vibrate even more, and we can see this wavelength that is being absorbed, or this frequency that is being absorbed of the infrared radiation in our spectrum. We'll see what a spectrum looks like very shortly. And what does this tell an organic chemist? Well, it tells us about the functional groups present in our molecule. Okay, so tells us about functional groups present in a molecule. Okay, so a very useful tool, I'm sure you'll all agree. Now, what does the data table for an infrared spectroscopy sort of experiment look like? Okay, so here is a table showing different kinds of bonds, and over on the left-hand side in the very first column, you've got lots of different types of bonds shown there. And what we want to focus on are these bonds that starting from, I can use my highlighter, starting from our carbon-carbon double bond all the way down to the OH bond of alcohols and phenols. Okay, so these are the very important bonds that we need to be able to identify in an infrared spectrum. The bonds that have wave numbers below 1500, in other words, these yellow bonds here, are in the fingerprint region. Okay? So the fingerprint region is used to identify molecules. If you carry out an infrared spectroscopy experiment and then compare the spectrum you get for your molecule with those in a database, you should then be able to get a perfect match or overlay, which allows you to identify your organic molecule in that way. If, however, you don't have your molecule already in a database, then you do need to use the wave numbers that I have highlighted in pink. So going from your alkene double bond to your OH double bond. So if I change highlight colors and consider these infrared absorbances here. Okay, so we've got the yellow fingerprint region, we can label. And then we've got the key bonds that we need to know about and be able to interpret correctly in our infrared spectrum. So alkene double bonds appear at about 1620 to 1680 wave numbers. and then you've got the carbonyl bonds, which absorb at about 1630 to 1820 wave numbers, and then you've got aromatic carbon-carbon double bonds, which can be distinguished from aliphatic carbon-carbon double bonds. Then you've got nitriles and CH bonds, as well as OHs and NHs and OHs of alcohols. Of course, the OH of the carboxylic acid is distinct from that of the alcohol or phenol. And so infrared spectroscopy can discriminate between these functional groups. Okay, so how do we use this table to allow us to work out what types of bonds, what types of covalent bonds are present, and what functional groups we've got as a result? So let's have a look at some example problems. Okay, so hopefully you should be able to see on your screen 3 examples of an infrared spectra, and you should be able to, if I use my highlighter to point these out, you should be able to see highlighted in yellow the x-axis for this first spectrum here, which tells us in wave numbers the wavelength of infrared radiation that is being absorbed, and therefore what bonds are present. Okay, so we've got wave numbers, and on the vertical axis you've got transmittance. Okay, so where you've got 100% transmittance, or in this case the scale is going up to 1, where you've got 1 or 100% transmittance, it means that there is no infrared radiation being absorbed, and therefore there are no bonds of significance as far as infrared spectroscopy is concerned. Like, so where there is a big dip in your spectrum, that is showing that there is an absorbance. So for instance, in this spectrum that we can see here, there is a big dip here. So there is that absorption at about 3,000, I'd say that's at about 3,000 to 300, maybe 3,200. The x-axis scale isn't particularly clear. Maybe we should do a bit of counting. So 2, 4, 6, 8. That's 2. Yeah, it's at about 3,300 wave numbers. So that is quite a significant absorption at that wave number, and we'll look at what that might mean as far as that spectrum is concerned shortly. And then there is a second significant absorption just before 3,000 wave numbers, and again that will correspond to a particular type of bond. Okay, and then there are no other significant absorbances sort of above 1,500. So everything else we can see here is in the fingerprint region, so we don't need to consider that in trying to work out what molecule this spectrum belongs to. So the yellow is the fingerprint region. If we were to compare this spectrum to spectra stored in a database and got a perfect match for the fingerprint region, then you would have identified this molecule, which would be matching whatever you had in your database. Okay, so in B, we've got quite a few absorbances to point out as well. So you've got this absorbance here, which is just before 3,000, and then going sort of lower at about 1,700, you've got this very strong absorbance. And again, those are the only 2 absorbances we've got above 1,500. Everything else is in the fingerprint region. So we don't need to worry about the yellow fingerprint region. Okay, and if we do the same for C, we've got a very strong absorption. If we pick a different highlight color, if we perhaps go to peach again, got a very strong absorption here. And again, we'll need to refer to our data table to identify what bond that is that corresponds to. Okay, so are there any other peaks above 1,500? So in other words, not in the fingerprint region. There is another strong absorption here, which I've highlighted in peach as well. So we've got 2 very strong absorptions above 1,500 and then you've got all your other absorptions in the fingerprint region. Okay, so what does this mean? Having identified these absorbances above 1500 meters, what we need to do is use our data table to allow us to identify the types of bonds present. So the data table I've shown in the middle of the screen. We make that a bit smaller and go back to A. But before we do that, our three possible molecules are written down for us. We're told that in no particular order, we've got ethanoic acid, we've got ethanol, and we've got ethyl ethanoate. So we've got a carboxylic acid, we've got an alcohol, and we've got an ester. So how do we use infrared spectroscopy to identify each of these three molecules? So if we take A for starters, you've got a strong absorbance at about 3,300. And if we look at our table, the strong absorbance at about 3,300 is for an alcohol OH. Okay, so if we take a highlighter and select. Okay, so that is representative of an alcohol OH, and we can label our absorbance as such. Okay, so an alcohol OH. Okay, and then if we look at the absorbance just before 3,000, that is typical of a CH, so about 2,850 to 3,100. Now, that isn't very useful for us because almost all the organic molecules that you will come across have got CH bonds in them. So if you're trying to distinguish between ethanoic acid, ethanol, and ethyl ethanoate, while yes, you can identify the CH absorbance, in practical terms, it's not going to help you to identify the structure or work out the structure of your molecule or of your molecules, given that they all have CH bonds. Okay, but I think it's still worth labeling all the same. So CH absorbance there. Okay, so with an alcohol OH and a CH. So it's looking good that A is ethanol. But let's have a look at B to see what we've got. So B has a CH as well. So if we label that, so that's a CH absorbance. And then if we look at the very strong absorbance at about 1700, that is a carbonyl absorbance there. So CHs and a carbonyl. There are no OHs present, so that's looking good for our ester. And finally, we've got C, which has a very broad absorbance from about 2,500. If I get rid of my peach highlighting for a second, we've got a very broad absorbance from about 2,500 all the way across to about 2,200. Okay, it's very broad. And if we look at our data table, you should be able to spot that the OH of carboxylic acids corresponds to this broad absorption, 2,500 to 2,300. Okay, so if we label that absorption, so that absorption here is the OH of a carboxylic acid. Okay, and you can see that this broad absorption for the OH of a carboxylic acid obscures the CH absorption that you would have as well for the carboxylic acid. So typically it will hide any CH absorptions that would be present. Okay, so based on our use of the data table, we should be able to say with quite a lot of confidence that A is indeed the ethanol or alcohol, so A, and we should also be able to see that B is our ester, so ethyl ethanoate, and C is our ethanoic acid. Okay, so as far as infrared spectroscopy goes, we want to look at the absorbances above 1,500 wave numbers. That those allow you to work out which functional groups are present, which covalent bonds are significant in your molecule. And when you've done that, you need to then label those absorbances with the appropriate functional group. And you need to, if you've got an OH, you need to specify what kind of OH it is. You need to say that it's an OH for a carboxylic acid, or that it's an OH for an alcohol or a phenol. Similarly, if you are looking at a carbon-carbon double bond, you need to be able to distinguish a carbon-carbon double bond in an alkene from the delocalized system you've got in a benzene ring, for instance, or other aromatic compounds. Okay, so that's a very sort of quick introduction to how you would use your or interpret your infrared spectra. Let's have a look at mass spectrometry. I guess at this point it would be a good idea to see if there are any questions. There are at the minute, so I will move on to mass spectrometry. So we're moving to the middle third of this session, where we will be looking at mass spectrometry. Okay, so what does mass spectrometry tell us? Mass spectrometer allows us to work out the relative formula mass, or the relative molecular mass of a compound. And as far as organic chemistry goes, we're most interested in determining the MR of our molecule. Okay, so we highlight in yellow. So determining the MR of our molecule, but also determining the MR of fragments that break off our molecular ion, and that allow us an insight into how the molecule is connected in terms of branching, for instance. Okay, so very useful for working out structure if we can determine what fragments are present. Okay, so now on the OCRA syllabus, you're not required to know how the mass spectrometer works. Simply you are required to use it to determine the MR, and also to work out fragments from organic molecules. And of course, you are required to know how to use it to determine the relative atomic masses based on the isotopic masses and abundances given to you by the mass spectrometer. Okay, so let's have a look at a typical mass spectrum, and let's use that to see what we can, how we can use that information to work out the possible structure of this organic molecule. Okay, so in this exercise, we're told that compound A has the following composition by mass. We're told that it's got 52.1% carbon, 13.2% of hydrogen, and 34.7% of oxygen. So we've got the data given to us from our elemental analysis experiment, so we can work out an empirical formula for this compound. Okay, so the information highlighted in pink allows us to work out the empirical formula. Okay, and then we're also given some information about the reactivity of this compound. We're told that this compound A does not react with active metals. So active metals such as sodium and potassium, these are quite reactive metals. And so we should be able to work out what type of functional group is present, if given that it doesn't react with sodium and potassium. Okay, so we've got the mass spectrum shown, and we've got the relative intensity here, which is up to 100, and the units of the relative intensity vertical axis are often arbitrary, not necessarily always up to 100. And then you've got the m/z value, which is the x-axis, and that is the mass divided by the charge for a particular fragment or for the molecular ion. And for the OCRA, of course, you're limited to molecules that form a molecular ion with a charge of 1 plus, or fragments with a charge of 1 plus. You wouldn't consider any peaks that are due to a fragment or a molecule that has a 2 plus charge, for instance. Okay, so the most important peak to pick out in your mass spectrum is the peak furthest to the right in your spectrum. So the largest M over Z value. Okay, so if we highlight that, and then we pick blue. Okay, so the largest M over Z value is that one there at 46. Note it's not the largest intensity we're looking for. We want the peak furthest to the right. Okay, so this is furthest to the right. It's also the largest M over Z. Okay, and this peak is significant because it is, or tells us, the mass of the molecular ion. Okay, so the molecular ion peak, or the M plus peak, is the one that's furthest to the right. And so this molecule has got an RFM or an MR of 46, which is incredibly useful if used in conjunction with the elemental analysis data. Okay, so we've also got some fragments in this spectrum, which we will look at shortly. But first of all, let's use the data we've got so far to work out the empirical formula for this compound. Okay, so we've got percentage composition of carbon being 52.1%. So we've got 52.1 divided by 12. And then we've got the percentage composition of hydrogen being 13.2. So 13.2 over 1, of course, is 13.2. And for oxygen, we've got a percentage composition of 34.7 divided by 16. Okay, so what we're doing is working out the moles of each of the different elements present. So 52.1, divide that by 12, and that gives us 4.34. And if we look at the oxygen, which is 34.7 divided by 16, that gives us 2.17. Okay, it's 2.17. Okay, so what we want, though, is a whole number ratio. We want the simplest whole number ratio. And to do this, we need to divide by the smallest number of moles at the next stage. So 2.17 divided by itself is, of course, 1. And then 13.2 divided by 2.17. We can work that out. 13.2 divided by 2.17. That gives us 6.08. And if we look at 4.34 divided by 2.17, that gives us 1.61. Okay, so we've got a ratio of 1.61 to 6.08 to 1, okay? And so that in itself isn't a particularly useful ratio to have. So if we multiply that through, hopefully by, let's have a look. So it looks like we may have, so we've got 52.1 for carbon. We should have a simpler ratio than what I've got here. So if we double check our calculation, we've got 52.1 divided by 12, and that should give us 4.34, that's fine. And then for hydrogen, we've got 13.2 divided by 1. So 13.2 divided by 1, which is equal to 13.2, of course. And then 34.7 divided by 16. And that should give us 2.17 again. Okay, so yeah, we've got the right numbers of moles, and then we need to divide by the smallest, so 2.17 being the smallest, we get 1, and 4.34 over 2.17, that is where the error has been made. So 4.34 divided by 2.17 should give us 2, so not 1.61. So hopefully I have illustrated here the importance of setting out your calculation neatly so that you can work out any errors or troubleshoot any errors that you make. Okay, so we've got an error in our calculation for 4.34 over 2.17. That should give us 2. And if we double check the number of moles of hydrogen, we've got 13.2 divided by 2.17. And yeah, so that gives us 6.08. So our empirical formula is effectively C2H6O. Okay, so we've got an empirical formula that is C2H6O, and then what we can do is see what mass that comes to, which would be 12 times 2 for the carbon, so 24 plus 6, which would be for the hydrogen, so we're up to 30, plus 16, which would take us to 46. Okay, so we can make the statement the MR of the empirical the empirical formula is essentially the same as the molecular formula. So our molecular formula should also be in this case C2H6O. Okay, so empirical formula is same as molecular formula. Because the reason we can say that is because when you add up the masses for the atoms in your empirical formula, they add up to the MR as given by your mass spectrum. Okay, so which is M over Z. Okay, let's write that. Let's make that a bit clearer. And let's say that it is the M over Z of the M plus all the molecular ion. Okay, so we've got the same empirical formula as the molecular formula, and as is using the information in the mass spectrum, we need to suggest possible structures of compound A. So C2H6O, so 2 carbons, an oxygen, and 6 hydrogens. The possibilities would include, if we make this a bit larger, or possibly running out of space, possible structures could be ethanol, and of course you could also have an ether. Now, given that we've been told that the molecule does not react with sodium or potassium, we can rule out ethanol, because ethanol would react with sodium or potassium in the same way as water does, to give you sodium ethoxide in this case, or potassium ethoxide. Okay, so the correct structure should be the ether. Okay, so that looks like it should be the right structure. What fragment is responsible for the peak at M over Z 15? So that is question D in this exercise, in this part D in this question. And so we're looking at this fragment ion here, and if we consider our candidate molecule, which is our dimethyl ether that I've highlighted in yellow, If we were to break off one of the methyl groups, the CH3 plus as our fragment, that would add up to 15. That would give us the fragment ion at M over Z 15. Okay, so the M over Z of 15 is equal to a methyl cation. Okay, so what we've done here is interpreted the mass spectrum for this molecule. We've used the largest M over Z value, or the M over Z value furthest to the right, to work out the molecular formula. That largest M over Z value is, of course, your relative molecular mass. And having worked out the empirical formula and then used this M over Z value, largest M over Z value, we can work out what the molecular formula is. Okay, so I have picked out a couple of questions from AS paper 2s in 2016 and 2018. We should have time to tackle one of these. They're quite similar questions, so I will do the first one from the 2016 paper, and then hopefully you can go away and tackle the question 7 of the 2018 AS paper 2. Okay, so at this point, I will very quickly check in on our Zoom group chat, and there aren't any questions, and so what we will do is carry on straight on to the practice exam question. Okay, so again, we've got data telling us about the percentage composition of the different elements in our mystery compound. So again, elemental analysis is telling us we've got 54.5% carbon, we've got 9.1% hydrogen, and we've got 36.4% oxygen. So that data can be used to work out the empirical formula for this compound. Okay, so again, if we highlight that and note the significance of it, so if we make that a bit bigger, there we go. Okay, so that allows us to work out the empirical formula. Okay, and then if we go down to the second of the two spectra we've been given, we can identify the largest M over Z value, so one furthest to the right, and we can also identify that little signal just one M over Z values away from our large M over Z value, largest M over Z value. That is usually due to a small amount of carbon-13 present in your molecule, and so we can disregard that M over Z plus 1 value. So this is going to be our molecular ion, okay, and should tell us our MR of this mystery molecule. So we can use that in conjunction with our elemental analysis data to work out the molecular formula. And before we do that, let's have a look at the infrared spectrum as well. And we've got this very broad absorption. If I pick the yellow highlighter, we've got a very broad absorption here, which is typical of our carboxylic acid OH group. Okay, so we can label that as such. So OH of carboxylic acid. We've also got just sort of tucked underneath is our CH there, okay, but not hugely important as far as determining the structure of this molecule. A more significant absorbance is the one at 1700, which is telling us that we've got a carbonyl group present. So again, worth annotating that. So C double bond O. And if you are running out of time, annotating your spectrum as I have done here is enough to get you all the marks you need as far as interpreting the signals correctly, the absorptions in your infrared spectrum. Okay, so let's then use all of this data to work out what our our molecule could be. So we've got 54.5% for carbon. So let's move over to the next page and carry out our calculation for the empirical formula. Okay, so we've got 54.5%. And then for hydrogen, we've got 9.1. And then 36.4 for oxygen. Okay, so if we divide by 12 and divide by 1, 16, 54.5 divided by 12, and that should give us 4.54, and we've got 9.1, and 36.4 over 16 is equal to 2.275. Okay. And then we want the simplest whole number ratio, and so we want to divide by the smallest number of moles. So 2.275 over 2.275, that is going to give us 1. 9.1 over 2.275, that is going to be 4 exactly. And then we've got 4.54 over 2.275. That should give us about 2. Some of it, probably 2 exactly. 4.54 over 2.275. And we've got 1.99, which will be all round up to 2. So, right, so we've got an empirical formula of C2H4O. Okay, and C2H4O, and we can work out what mass this comes to. So we've got 12 times 2 for your carbons, which is 24, plus the plus the hydrogens. That takes us up to 28. So 4 hydrogens, and then 28 plus 16. Okay, so 28 plus 20 would be 48, and then if we take out 4, we've got 44 as our empirical formulas, empirical formula mass. Okay, so our MR is equal to, we haven't quite worked out what the MR is equal to. If we go back to our mass spectrum, our MR looks like it is 88. Okay, so we've got 90, and then counting 2 back to that signal, we should have 88. So the MR is 88. And so if we divide 88 by 44, we get 2. Therefore, the molecular formula is going to be 2 times C2H4O, and so we've got C4H8O2. Okay, so that is our molecular formula. Okay, so let's go back to the question. So we've got data given to us, and we've got a secondary carbocation is responsible for the peak with the greatest relative intensity. Okay, so there's some more data here that we need to use to work out the structure. The secondary carbocation is responsible for the peak with the greatest relative intensity. So the peak with the greatest relative intensity is that one there. Okay, and that peak is at 1, 2, 3 is a 43. So let's annotate that as well. So 43, and that should be useful in working out the structure. So let's go back to our question. So in your answer, it says identify compound C. Okay, so we've worked out that it's C4H8O2. We've worked out that it's a carboxylic acid. We also know that it has a fragment ion that is a secondary carbocation. Okay, so let's put all of this together and work out the structure. So We do the structure in blue. We've got a carboxylic acid group, so C-double-bond-OH. We know that there are 4 carbons altogether, and that we do have a secondary carbocation. So we work backwards to look at the potential secondary carbocation. If we were to break that bond there, you would be left with a fragment ion that was the fragment ion that would be that ion there, and that would be a secondary carbocation. And that secondary carbocation has got 3 carbons, so it's got C3, and it's got 1, 2, 3, 4, 5, 6, 7 hydrogens. Okay, so C3H7 plus. If we worked out the mass of that, so 12 by 3 is 36, and 7 hydrogens, so Mr is equal to 43. So we can be confident that we've got the correct structure there. So we've got our carboxylic acid OH, which we identified from our infrared spectrum. We've also got the carbonyl of our carboxylic acid, and we've got in blue this secondary carbocation fragment. Okay, so that is the structure for this mystery compound C. Okay, so what I'd urge you to do is to go away and tackle what is quite a similar question, working out the empirical formula and molecular formula, and using the mass spectrometry data you've been given to work out the molecular formula, and then any fragment ions that you may be required to identify. Okay, so at this stage, I will bid you farewell. It's been a pleasure to go through infrared spectroscopy and mass spectrometry with you. As usual, if you've got any questions, do drop us a line at Boost, and we will be very happy to get back to you with answers to your questions. Hope to see you soon. Hope to see you next Sunday. Thank you very much for joining me, and good night.